So in this lecture, we're continuing on looking at the properties of relations. In the previous lecture, we looked at the property of a relation being reflexive, and now we're going to look at the property of a relation being symmetric. Okay, so if a relation is such that whenever A is related to B, then B is also related to A, so that either nodes are unconnected, so they're not related at all, or a double edge connects the nodes, then OR is said to be symmetric. Now, the best way to explain symmetric and not symmetric is Facebook and Twitter. So on Facebook, when you're friends with someone, you're friends with them, they're friends with you. That's a symmetric relation. Whereas on Twitter, you can follow someone. That would be an edge going from your node to their node, but they mightn't necessarily follow you. So for example, neither of the two relations presented in this section above are symmetric. So look at the first one. C is related to B, but B is not related to C. So this is not symmetric. You need a double edge. You need an edge going backwards for it to be symmetric. And the thing about it is that it's not enough that one double edge makes you symmetric. So for example, say that B was related to C, so we had this double edge. That doesn't make this relation symmetric. It's symmetric if every single time a node is related to another, or an element is related to another, that the relation goes back the other way. The other thing that's fine is, say 3 and 4 here are unrelated. That's not an issue. The issue would be, say in the second one, 2 is related to 1, but 1 is not related to 2. So they are examples of not symmetric relations. So an example of a symmetric relation is siblinghood. So people with the same parents or whatever. So take any set of people P. So for example, we're going to take a set parent 1, parent 2, child 1, child 2, and say that two people are related if they are siblings. So if they're brothers or if they're sisters or whatever. So the digraph should look something like parent 1, I'm just going to write P1 for parent 1, parent 2, and then child 1 and child 2. So we have, so you connect, people are related if they are siblings. Now there's a question, are you your own sibling? We'll say no, you're not your own sibling. Okay, so child 1 is related to child 2 because they have the same parents, and also child 2 is related to child 1. So that's how you might draw the double edge, or alternatively you could draw one edge going this way and one edge going back. So this is a symmetric relation. It doesn't matter that these aren't relations are related. The only thing is that whenever there is an edge, it is a double edge. You can in fact have the empty relation where nothing is related to, like for example, if they're just 4 random people that aren't related at all, then the digraph would just be, there'd be no edges at all. That's perfectly symmetric. All you have to do is, whenever there is an edge, you make sure that it is a double edge. So, and it's worth commenting, this is not reflexive because we're saying that people are not their own sibling. Okay. So, if then this last one is the hardest one. Okay, if we have a relation or, if a relation or, sorry, English isn't great there. If a relation or is such that whenever A is related to B and B is related to C, then A is related to C. And this is what's called transitive. Now, there's kind of different ways of talking about it. Probably the easiest thing is think of less than. So if A is less than B and B is less than C, then A is less than C. Now, you can't mix up the arrows or the order. Like you can't have, like say A related to B and C related to B. It has to be exactly like this, A to B, B to C. And if it's a transitive relation, whenever you see this, you will also have that A is related to C. So in this case, whenever you have a pair of arrows, you have an arrow going from A to C, and we'll see that in a minute. I would say that transitive in the digraph is like that there's always a shortcut. Okay, so siblinghood is not a transitive relation. I'm not sure about that, and my issue with siblinghood there is that we haven't defined what sibling. Does it mean that you have both parents the same? Then it would be transitive, wouldn't it? So if I have exactly the same parents as a second person, and the second person has exactly the same parents as the third person, then the first person, me, and the third person also have the same parents. We would be siblings. But if you define siblinghood to just have one common parent, then it wouldn't be transitive. So, for example, I've got a half brother, and say, for example, if his mother had another child with a different person, then I would be related in this sense with my half brother, and my half brother would be related with that other child, but I would not be related to the third child, so it wouldn't be transitive. But that's about defining siblinghood carefully, and we haven't done that here, so we won't worry about it. I want you to determine yourselves whether these are transitive. Just have a think for yourself. Apologies about the dog barking. I can't do anything about it. Hopefully he stops soon. So a good example of a transitive relation is less than. So let's take the set 1, 2, 3, 4, and let us draw the digraph for that. Okay, so we're going to draw an arrow. So two things are related if the first thing is less than the second. So we know that 1 is related to 2 because 1 is less than 2. We might write down the ordered pairs afterwards. We know that 1 is less than 3, so we'll draw an arrow between them. And we know that 1 is less than 4, so we'll draw an arrow between them. Then 2, now it's this without the equals is strictly less than, so 2 is not less than 2, for example. 2 is less than 3, and 2 is less than 4, and finally 3 is less than 4. But 4 is not less than anything else. We may as well write down the ordered pairs here. So we'll call the relation less than, equal to, set of, so just all the ordered pairs. 1 is related to 2, 1 is related to 3, 1 is related to 4, 2 is related to 3, 2 is related to 4, and 3 is related to 4 as well. Okay, now this is transitive. It's probably hard to actually prove it. I mean, you'd actually prove this with algebra, for example. We won't. I'm just going to say it is transitive. Like if you look at any pair, like I think we can just look at all possibilities. So 1 is related to 2 is related to 3. There's a shortcut. 1 is related to 3. 1 is related to 2 is related to 4. There's a shortcut. 1 is related to 4. 1 is related to 3. 3 is related to 4, and there's a shortcut. 1 is related to 4. Now starting at 2, 2 is, and you can just go through it. There's only finitely many, so you can see that it always works. Okay, so this is transitive. Now let's show it's not reflexive because you can say there's not a loop at 1, there's not a loop at 2, there's not a loop at 3. Now to be not reflexive, it just has to fail once. Like if there's loops at 2, 3, and 4, but not at 1, it's not reflexive. Reflexive means every single node has a loop. Every element is related to itself. So it's not reflexive, we can say, because 1 is not less than 1. And it's not symmetric because 1 is less than 2, but 2 is not less than 1. To be symmetric, if you have an arrow from 1 to 2, you have to have one going from 2 to 1. The less than or equal to is reflexive because 1 is less than or equal to 1, 2 is less than or equal to 2, 3 is less than or equal to 3, 4 is less than or equal to 4, but it's not symmetric because 1 is less than or equal to 2, but 2 is not less than or equal to 1. Okay. So now I'm going to draw something here. So here's a relation, PR, RS, SP, and it is transitive. So let's see. Yeah, okay. Well, I'm not sure is it transitive. is this transitive? Maybe not. So we have P or S. This is a relation. Now there is a problem here because I've used or twice. That's not good. So I'm going to call the relation, let's call it R1. Yeah. Okay, so we've got P is related to R. We have R is related to S. And S is related to P. Now the question is this transitive? So the best way well, it's easier to find, say, when something is not transitive, because all you have to do is find something that doesn't have a shortcut. So we have R is related to S, S is related to P, but R is not related to P. So you can go from here in 2, but you can't go in 1. So it's not transitive. So not transitive, you have R is related, and I'm going to have to write this R1, sorry, it's very bad notation. I'll do a line underneath it as well, just to let it. So R is related to S, and S is related to P, but, so if it was transitive, if R is related to S, S is related to P, you'd have R is related to P, R is not related to P. You don't have RP, you have PR. Okay. Now you can have a think about what actually this represents, by the way. It actually represents something in the real world, the R, P, and S standing for something. You can have a think about it. And if you figure that out, you can see something interesting in the next section, which is a further remark going a bit further. And it's about non-transitive dice. So these would be a triple of dice. And in a certain sense, the first dice is better than the second dice. And the second dice is better than the third dice, but the first dice is not better than the third dice. So those of you who might be into some kind of gaming might be interested in this. Okay, so that's that. Right. So I think what we've done is everything that's needed for the first test, and we are going to. Should we finish here? Yeah, we'll finish here. We'll just talk about the last thing. Okay, so relations that are reflexive, symmetric, and transitive. So everything is related to itself. Whenever something is related to something else, it works both ways. And transitive, you got these shortcuts. This is an equivalence relation. Now, it's said to be called an equivalence relation because it looks like equality. Now, I think maybe the best way to show this is as follows. Well, it's hard to know what I want to write here. So, okay, let's just write down. I'm not sure. Okay, let's just write down S is equal to, so let's say 0, 1, 2, 3. And we'll say that A is related to B if the difference between them is 2. We'll just see what happens here. Hopefully this actually works. Okay, so let's draw this digraph. Well, maybe we'll write down the relations first. So the ordered pairs. So the ordered pairs. Now, is 0 related to 0? Yes, because 0 minus 0, oh, sorry, this should be, is a multiple of 2. Yeah. So if the difference between them is a multiple of 2. So 0 minus 0 is 0 is a multiple of 2. So 0 is related to 0. 0 is also related to 2. Okay. Because the difference between them is 2 is a multiple of 2. You've also got 1 is related to 1. 1 is not related to 2 because the difference between them is 1 is not a multiple of 2. 1 is related to 3. You also have 2 is related to 0. You also have 2 is related to 2. You also have 3 is related to 1. And 3 is related to 3. then we'll draw the digraph of this. Hopefully this I can kind of explain why this is kind of equality. So 0, 1, 2, 3. We'll explain it a lot better afterwards, where we will have examples, obviously. So, okay, 0 is related to 0. 0 is related to 2. 1 is related to 1. 1 is related to 3. 2 is related to 0. 2 is related to 2. I don't think this explanation is going to go very well. 3 is related to 1 and 3 is related to 2. So this one is an equivalence relation. It's reflexive because there's a loop at every node. It's symmetric because every single edge is a double edge, and the loops are fine because if you think about what symmetric says, it says if A is related to B, then B is related to A. So we got 1 is related to 1, then automatically 1 is related to 1. So no issue there. And it is also transitive. You probably have to do a little bit of work to show that it's transitive, but take my word for it. So the idea is that 0 and 2 are kind of equivalent, and 1 and 3 are kind of equivalent. They're kind of the same thing. Does this explain it? We have to say no, and I think I've failed in this. But anyway, so this is an example of an equivalence relation, and hopefully we might get a. Yeah, I think I have more explanations in the next chapter.